Today we will continue our discussion on the nuclear models. So, in the last class we had studied some the shell model, and we said shell model is a good description of the nucleons, especially when it comes to odd A nucleons, the nucleons with odd atomic number, which means either the proton or the neutron number is even, while the other is odd. And in the extreme independent single particle shell model, we said all the properties of the nucleus like this is described or given by the unpaired single neutron or proton in the particular nucleus under consideration. Which also says that all the neutrons and protons try to pair with each other, which means that if there are two neutrons in the nucleus, they will pair with each other, and there will not be any kind of, they will try not to interact with the outside world or outside the system and become kind of an inert thing. So, if there are 11 neutrons and then 10 neutrons are paired, and there is one neutron which is left without any pair, and this neutron will dictate the properties of the nucleus concerned if the protons are already paired with each other. We saw that not only that the spin and angular momentum of the spin and the parity of the nucleus in the ground state, that can be explained very well in such cases with odd neutron odd atomic odd mass number. And but if you look at the excitation states or excited states of these nuclei, that also can be very well accommodated within this shell model in its extreme independent version. And towards the end of the discussion, we had last time, we said in some cases, some of the excited states cannot be accommodated just considering one neutron or proton, but we may actually think about say 2 or 3 neutrons placed in different shells and take the combined effect of these, as we saw in the case of oxygen and fluorine in the last time. In this, so we will continue with this discussion, and then we see that there are some limitations certainly with this extreme independent version of the shell model, because it is too restrictive. It is not very realistic to think that only one particular nucleon which is unpaired is causing all the properties of the nucleus. So, we will take up an example for here, which clearly illustrates that we will have to do slightly better than this extreme independent shell model. So, for example, if you take a calcium 41, the calcium has 420 protons in the nucleus, and depending on its isotope, it will have 40, 41 or 43 or some other number around that total number of nucleons in it. So, if you particularly take calcium 21, it has 21 calcium 41 sorry, there are 21 neutrons in it apart from 20 protons, and if you take calcium 43, it has 23 neutrons in it. This proton distribution, if you look at the shell model, the 20 is a magic number for us. We know that from experiment, as well as our model also can predict that. Corresponding to this 20, there is a closed shell, and therefore, the protons are completely filled in that closed shell, and then we do not expect them to be actively participate in any interactions or produce or give rise to any particular property of the nucleus in that way. So, now this distribution of the neutrons, when we consider calcium 43 has 23 neutrons which are distributed in these shells, and 20 of them are in the inert core with the magic number filling the magic number 20, and extra 3 neutrons are placed in 1f7 by 2 when we consider the Woods-Saxon potential with spin orbit coupling in it. And if you look at the calcium 41, it has a similar kind of distribution, proton exactly the same kind of thing as the calcium 43. For neutron distribution, there are 21 neutrons and 20 neutrons are again placed in the inner core, filling the magic the shells with magic number 20, and one extra neutron is placed in 1f7 by 2. So, if you look at calcium 43 and 41, then you see that in each case there is one unpaired neutron in the 1f7 by 2, and we will imagine that this is reflected in its spin parity assignments of its ground state as well as some of the at least low lying at least the first few excited states. Alright. The prediction for the ground state IP, the spin and parity, is 7 by 2 minus in both case. Okay. And let us see what is the kind of observation that we have regarding the excited states. When we look at the excited state, we will see a little different picture than what we actually would expect compared to the within the shell model, single particle model. In the case of calcium 41, we see that there is one extra nucleon which is there outside this magic number closing the inert core, and it is and the excited states like there is first excited state 3 by 2 minus, which can be very well explained by considering the extra nucleon, the neutron absorbing the energy or taking the energy and jumping to or excited to or going to the state P 3 by 2. P 3 by 2 has L equal to 1, therefore, odd parity state, and J is 3 by 2, therefore, the spin of the nucleus corresponding to this is expected to be 3 by 2, and then we see that there is a 3 by 2 minus state, and there are other states like 3 by 2 plus etc., which may be again accommodated by saying that the 1 d 3 by 2 breaks the pair and then take it to 7 by 2. So, that the neutron in the 7 by 2 f 7 by 2 is paired, and you can have you have now an unpaired neutron in the 1 d 3 by 2, and therefore, it is in the nucleus is in the I equal to 3 by 2 and P positive corresponding to D shell, which has L equal to 2 state 2, which is okay. But when we look at calcium 43, the case should have been similar if all is well, or if we agree with the single particle shell model. There is one unpaired neutron in the 1 f 7 by 2, which could be taken to 1 p 3 by 2, okay, as the first excited state. But and the energies should also be similar. to excite one neutron from 1 f7 by 2 to 1 p3 by 2. There is no breaking of pair in either case as per the model goes. It is just taking that particular neutron in 1 f7 by 2 into 1 p3 by 2 in both cases. But contrary to this expectation, we see a very low lying, less than half of the excitation energy corresponding to calcium 41. Calcium 43 has very low lying 3 by 2 minus, but that is not the first excited state either. There is a 5 by 2 minus even before that. How do you accommodate that? And there are not only these, but many other low lying excited states, 3 by 2 plus, 5 by 2 plus, 11 by 2 minus, etc., even before you reach 2 MeV, which is needed to break a pair of the nucleons inside the nucleus as expected. So, we need to actually modify it a little, our model, and let us say we want to actually consider the case not just of the single neutron which is unpaired in that outer shell, unfilled or not completely filled or partially filled shell, but we will let us take all the neutrons in that partially filled 1 f7 by 2. In this particular case of calcium 43, there are 3 of them, and we will consider all the 3 of these things. Okay. And then again excited state could be 3 by 2 minus, as I said earlier, and the observed ones are like observations are like this, but then the expectation with this new arrangement or new interpretation that or the relaxation that is made to the shell model, that it is not that the two of the nuclei in the outer shell 1 fs to 7 by 2 is paired, but all the 3 of them are treated at the same kind of footing, and we can consider the effect of all these 3 together. So, basically when we compute the angular momentum, total angular momentum of the nucleus, then you will have to consider all the 3 neutrons, which means there is a 7 by 2 plus 7 by 2 plus 7 by 2 that you have to add according to the angular momentum addition rules, and then that will give you, let us see what it will give you. Basically, you are adding 7 by 2 and 7 by 2, that will give you 0, 1, 2, 3 up to 7, because 7 by 2 plus 7 by 2, the maximum is 7, and 7 by 2 minus 7 by 2 is the minimum when you add this vectorially or as per the angular momentum addition rules. So, that will give you a 0, and with each of these you have to add now 7 by 2. So, that will give you, say for example, you take 0 and then consider this, that will give you 7 by 2, 1 and 7 by 2, that will give you 6 by 2, sorry, that will give you 5 by 2 and 7 by 2, 2 that will give you 2 minus, that is equal to 3 by 2, 5 by 2, 7 by 2 and like that. So, when you consider 3 for example, you will get 3 plus, say for example, 3 by 2 plus 7 by 2 will give you, sorry, not 3 by 2, it is 3 into 3 plus 7 by 2. So, that will give you either the minimum value is half and the maximum is 3 plus 3 by 2 is 10 by 2, 10 and a half it is 21 by 2, all right. And there is a 7. So, 7 is basically, so this is, So, this will give you actually the minimum, and you have now 7 plus 7 by 2, that will give you 14 by 2 plus the maximum is 14 by 2 plus 7 by 2 is equal to. Okay. So, this is the absolute maximum that you can get from this 7 by 2 plus 7 by 2 plus 7 by 2, and in the case of minimum it is 1 by 2. So, you can say that with this combination you will have basically a minimum of 1 by 2 and a maximum of 21 by 2. Okay. And obviously, all of these what excited states can be accommodated within any of these. So, the excitation energy is not really taking the electron from somewhere to somewhere, some higher state, but within that it is actually getting a higher energies, right. And so, this is kind of slightly a different approach that you have to consider compared to the extreme independent shell model. Okay. Now, the positive parity and other of these positive parity systems may be accommodated by considering a 1 d3 by 2 or 1 d5 by 2, breaking a pair and then going into that. But the catch there is that these are very low lying, and the energy needed to break one pair of such a nucleon pair, neutron pair is about 2, and then you would expect an excited state with 3 by 2 plus or 5 by 2 plus have with energy around 2, maybe a minimum at least 2 by about 2 MeV, whereas here it is much less than that for 5 by it is about half of that for 3 by 2 and 5 by 2 has a little more than that. Okay. So, we need certainly to go beyond this shell model kind of a description to accommodate everything even within the excited states, I mean even within the observations of excited states. Now, what about the odd A nuclei with Z number of proton, odd Z number and odd AN values? In this case, we have to come to some kind of a conjecture, and then it could be that a proposal could be that the J values of both the unpaired, each case when we consider the proton and neutron, there is one unpaired proton, there is one unpaired neutron. So, consider the total J value of both of these and then consider that as the total energy, angular momentum of the nucleus. Say for example, in the case of lithium 6, you have 3 proton, 3 neutrons, and both protons and neutrons are in the same one p 3 by 2 state, the unpaired single neutron, and you can ask the question, what is the spin value? Spin, as we said, is a combination of, so J p here is equal to 3 by 2 and J n is also equal to. Now, 3 by 2 and 3 by 2 has to be added. So, J p plus J n will give you 3 by 2 minus 3 by 2 is 0, which is the minimum, and 3 by 2 plus 3 by 2 is 3, which is the maximum, and in between there are 1 and 2. So, the possible I values are 0, 1, 2 or 3, and parity has to be is a multiplicative quantum number. So, what you have to consider is what is the angular momentum of this single unpaired proton, which is equal to 1 because it is in the p state, and L n is equal to 1 again because that is also the neutron is also in the p state. So, when you take minus 1 power L p, that will give you 1, okay, and minus 1 power L n, that will also give you minus 1, and together when you take the product of these two, that will give you a positive this one, all right. And what is observed, you could ask, the ground state is all right, it is observed with spin 1 and parity plus, which is accommodated within this. Okay, we are one of the possibilities. Another example that you can take in the same similar situation is aluminum 26. So, it has 13 protons and 13 neutrons in it. So, you can ask the question again, what are the spin values? Let us see. So, it is J p equal to 5 by 2, it is in the 1 d 5 by 2 state, and J n is equal to 5 by 2, because you have again 13 neutrons, and 5 by 2 minus 5 by 2 is the minimum I, which is equal to 0. I max is going to be equal to 5 by 2 plus 5 by 2, and that is equal to 5. So, I, the possible I values are 0, 1, 2, 3, 4 and 5, and parity L p is equal to 2 and L n is also equal to 2. That will give you parity equal to minus 1 power 2 into minus 1 power 2, which is equal to plus 1, right. So, parity is plus 1, observed I p is 5 plus, well, 5 is certainly there in that, that is accommodated. How does one prefer 5 instead of 4, 3 or 2 or 1 or 0? We need to look at further details about this thing, the wave function, etc., and then it is slightly beyond the discussion that we have here. All right, I think we will not go into the details of any of this. Actually, for those of you who are interested, certainly there are enough books, including the textbooks that we are considering, giving a lot of details of calculations, and various other examples are also discussed. Let us go on and then consider the next the other kind of nuclei with again even A, but this time even Z and even N, both N and Z are even. What about that? As per the extreme independent shell model with single particle unpaired neutron dictating the properties of the nucleus, okay, we expect I p to be 0 and positive, because there is no unpaired neutron, no unpaired electron. Well, and if you look at the even nuclei, most of them agree with this thing. I think almost all of them which are observed agree with this, and that is okay, it is confirmed very well. And let us look at the excited states. Say, consider the example of oxygen 18, Z is 8, which is a magic number, and therefore, we think that will not be coming into play when the properties of the nucleus is concerned, especially in the case of excited states. But neutron number is 10 in this case. So, the configuration is 2 neutrons in the lowest 1 s half, 4 neutrons in the next 1 p 3 by 2, 2 in the 1 p half, completing the inert core with magic number 8, inner core, and then you have 1 d 5 by 2, which has 2 neutrons in it. I p is anyway 0, there are no unpaired this ones. How do we excite this? One way to excite it is to split the pair in the outer shell, incomplete shell, 1 d 5 by 2, and take that to the next, take one of those neutrons to the next level, which is 2 s half. So, you have here one neutron in s half and one neutron in d 5 by 2, similar to the additions that we had done in the previous slides. Yeah? we will see that a combination of 1 by 2 and 5 by 2 will give you 2 or 3. Okay. So, that will give you a 2 or 3, and what about parity? Both are in the L equal to, or one is in the L equal to 2 state, the other is L equal to 0 state. Okay. Minus 1 power 2 will give you 1 plus 1, minus 1 power 0 will again give you plus 1, and product of these two will give you plus 1. So, the parity is positive. So, we expect first excited state to be either in 2 plus or in 3 plus, or all right. What other possibilities are there? Well, one could actually break 2 protons in the 1p half, although that completes the magic number, magic shell 8, we can break one there, giving lot of energy, and then take that to the 1d 5 by 2. So, that will give you 2 minus 3 minus 2, because it is again j equal to 5 by 2 and j equal to half states, similar to the previous case. But in this we have one of that is a odd parity level. So, that combination will give you an odd parity, or we could actually take the 5 by 2, break the 5 by 2 neutron again, and then take it to not s by s half, but you have enough energy to go up to d 3 by 2 say. In that case, it will be in 5 by 2, 5 by and 3 by 2 combination will give you 1, 2, 3 or 4, all right, and parity is positive because both are even parity states. Another thing could be that both of these 2 neutrons in 1 d 5 by 2 goes to 1 s half, and then that will have a excited state with 0 plus perhaps. Well, you could also take the 1 p half, break that, take it to d 3 by 2 instead of d 5 by 2, or you could take it to actually s half. Okay, you could take it to any of those things. So, the combination will here be either 1 or 2 minus. So, these are some possibilities. There are other possibilities as well that you can think about. So, for example, in this case we have, in the last case we have actually jumped from one way s half. We could actually go to s half instead of d 3 by 2, and there it will be 0 minus and 1 minus. All right. Let us see what we have observed. Okay. This observation result is taken from this particular reference given here, and the observation is that indeed the ground state is 0 plus. There is around 2 MeV, there is a 2 plus excited state, and then there is a 4 plus and 0 plus, 1 minus, 2 plus, etc. So, one thing is that we do not see any 2 minus, 3 minus in the low, in the first few excited state, all right, and 2 plus is obviously could be accommodated very well within this, but then, and it also corresponds to breaking energy is 2 MeV, which is all right, but then the other states are all around 4 or 3.5 4 MeV. Okay. What is special about this 2 plus? I mean, we do not see anything special that we could accommodate to this here. Okay. So, now there is this suggests that again we have to slightly go beyond the single particle shell model and accommodate other aspects of this. When we actually consider other even nuclei, many of these even nuclei with even number of protons and even number of neutrons in it, they all have this same kind of feature. They have all one single 2 2 plus state at low energies. So, in the case of tin, for example, even at 1 MeV, which is half the energy needed to break a nucleon pair, and there are lot of many states around 2 MeV, but this is a single isolated state, first excited state, very low lying excited state, and this is kind of a common feature of many such even nuclei. So, suddenly one has to actually to accommodate this thing, one has to go beyond this thing, and one way people think to accommodate all this is to consider some apart from the either along with the single particle the shell model description, you consider also effect of other nuclei, some kind of a collective behavior of these nuclei, or for the even nuclei, in fact, people worked without this shell model, considered only kind of collective models. Okay. So, in such cases, what happens is that the excited state will have other modes to be considered, collective modes to be considered. We will come to that in a little moment. And then there is there are other properties like the magnetic dipole moment, quadrupole moment, electric quadrupole moment, etc. What are the predictions of these there? There again one has limited predictability or limited explanation that the shell model can give. For example, the magnetic dipole moment mu is equal to the nuclear magneton divided by H cross and GL times expectation value of LZ plus GS times expectation value of SZ. Okay. This, but remember we have included the LS coupling in our model. So, LZ and SZ are not really the good quantum numbers. I mean the system will not have any definite LZ, physical states will not have any particular LZ or SZ values, rather it will be having the total angular momentum J and JZ values. So, we have to rewrite this in terms of J and JZ. So, basically you can write LZ as JZ minus SZ. So, this will turn out to be so. Then now finally, this will be JES into LZ minus SZ when you write it in this fashion, and sorry, JZ minus, and this JZ is LZ plus SZ. So, LZ is JZ minus SZ. So, there should be a GS minus GL term there and SZ. Now, SZ itself is not a good quantum number, but you can write SZ in terms of J, L and S values. So, we will not go into the details of that, but you can do that yourself. It's simple quantum mechanics. Now, one can actually for each of these cases, each of these nuclei, you can try to compute this mu, expectation value of mu, and compare it with the experiments. And when we do that, we see that they agree roughly, but not quite well. So, there has to be some kind of corrections that we have to think about, additional inputs needed to explain everything. So, it is roughly the same, roughly the expected value, but not completely. Similarly, for the quadrupole moment, when you go to the quadrupole moment, what happens is electric quadrupole moment, again you can compute these things, we will not go into the details, but you will see that here it fails even, the predictions are even worse than the magnetic dipole moments predictions. So, clearly one has to go beyond the shell model. Obviously, I mean this was a simple, very simple model. So, we are not surprised that in fact, we should be very surprised that a lot of these properties, considering the spin and parity of the excited states as well, are explained very well in this within the model. Okay. And certainly one has to accommodate other aspects of the nucleus into the model. Okay. So, the collective models are take a different philosophy. It says that it is not any particular nucleus or nucleon is not special. So, everything is collectively giving rise to these properties. Okay. And say for example, the liquid drop model. In fact, when we discuss the semi empirical mass formula, we had somewhat considered this kind of a nucleus. The nucleus which is a kind of a uniform distribution of this one. We did not really talk about nucleons inside that, the granule, the finer details of this one. We said that take it as a kind of a sphere or a liquid drop, and then think about what is the density of that, what is the volume term that will enter in the mass or binding energy, and what is the surface term that will come in there, etc. Okay. We did not talk anything about the nucleons inside. All right. So, and the constant density which is experimentally observed can also be explained very well within the liquid drop model, for example. But liquid drop model cannot explain all the excited states again, and there are various problems with that. Okay. But so there are variations of this. There are other models like Fermi Gas Model, considering all the nucleons as independent objects like gas molecules, okay, non interacting gas molecules, and confined in a volume, and you can work out the details of this model and then see how it works. Okay. Something which confines them to the model, the particular volume is what the Fermi gas model will consider. Then there are other models, generalized collective model, density function model, etc. I am just giving you the names so that you can go up and look up these models and then understand them yourself. We will not go into the details because that is beyond the scope of this course, but we will say certainly that all these models will contribute better understanding of the experimental observables, like observations like say the excitation states of even nuclei. Especially for the even nuclei, these collective behavior is more prominent compared to odd nuclei or odd nucleons, the nuclei. Yes. Then actually in a case of a realistic model, one need to perhaps take a combination of both of these things. Some kind of a uniform approach need to be considered. One has to, I mean, one cannot actually say that odd nucleons, there are, I mean, say let us say roughly we can categorize these two. One type of nuclei where we can consider the property, the model corresponding to that nucleus as kind of shell model, and the other kind of nuclei, say even nuclei, considered with a model like collective models. Most of the time what you will have to do is to actually take combination of both in realistic models. Say for example, in the case of single particle shell model, we do not really worry about what is the picture, what is the contribution of the nucleons in the completely completed shells. If you want to consider their role also, then one way to think about is to consider some kind of a core, inner core, which collectively behaves like a collective body, gives contributions as a collective body to the nuclear properties. How does it give contribute to the energy levels? For example, you could think about vibrations of this collective body. A liquid drop or a sphere, which is not a solid sphere like a rigid sphere, it can actually vibrate. It can also rotate. Well, a rotation, if it is a completely spherical symmetric body, then rotation may not give you any this thing, there is no axis of rotation. So, symmetry will tell you, I mean, you do not expect anything. Whereas, most of the nuclei, especially heavier nuclei, are all not completely symmetric as far as we know. They deviate from sphericity, and thus we can also think about rotational modes for this. So, now in this way we can accommodate some of the observations discrepancy that we had in the case of excited states of many nuclei, especially in the case of even n nuclei, even nuclei. Maybe the contribution of these vibrational modes and rotational modes can give rise to this or can explain the disparities. Indeed, these approaches are considered, and it is found certainly that the vibrational and rotational modes certainly have to be taken seriously in the case of many nuclei, okay. And they, I mean, we can actually work out an explanation for many of the observations better than the the explanation purely based on shell model or collective model that way. So, some kind of for realistic models, one will have to actually consider kind of a combination of this thing. We will not be able to go into the details of any of this thing. Okay. So, idea is basically to give you a flavor of the nuclear model, okay, and a starting point from where you could take off on your own. So, you can certainly go and then try to understand this in more details. Okay. So, for the time being, we will actually stop our discussion on the nuclear models here. We will end with two exercises that you could try on your own. There are many other exercises that you can think of also, and also available in the textbooks that we have referred to. So, let us consider these two questions. One is that you take chlorine 13, it has 17 protons and 16 neutrons. So, find out how in an extreme independent shell model, how does the electron and proton. So, proton and neutron are distributed in different shells. Then what is your prediction corresponding to the I and parity, I value, the spin and the parity of the excited the ground state, the first few excited states, etc. Okay. You can easily work that out. And you look at Ti 43, 22 protons and 21 neutrons in it. So, 21 is actually number 1 more than the magic number 20. So, you would so today's discussion is valid there, saying that collective behavior is important there. So, you can check this out, what are the values of these I values and p values, the spin and the parity values for the ground state as well as excited state that you expect. Okay. In fact, it is given that there is a low lying 3/2 plus and 3/2 minus. How do you accommodate that within this? That is what you can think about. The hint is you can actually, you also have 2 protons in the shell outside the just above the magic number closed shell with magic number 20. So, you may also consider these 2 protons going slightly beyond the single particle shell model approximation, considering multi-particle shell model, but okay. So, you can think about that in that direction, and then see if you can accommodate 3 plus and 3/2 plus and 3/2 minus in this thing.